talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolvin. Today we're going to talk about pressure, and it's part 5 of my Newton's second law series. So the main idea for this video is for constant force, an increase in area of contact will result in a decrease in pressure. Whoa. Okay, let's dive into that a little deeper. So the amount of force per unit of area is called pressure. And here's our formula that we're going to use to calculate pressure. Force you can only use this formula when force is perpendicular to the surface area. In more advanced physics classes, they'll take care of how to figure out how much force and what pressure is in other situations, but for us, we're only going to worry about it when it's perpendicular to the surface. Now, let's take a look at this formula. Capital P for pressure. F is going to be force, as always, capital F. And this time we have a capital A. And capital A is really important because lowercase a represents what? Oh, you guys know, it's acceleration. So rather than saying pressure is force divided by acceleration, you have to use a capital A. So that's kind of an important thing. The size and the capitalization matters in physics formulas. Okay. So P is pressure. Capital A is the area over which the force acts, and you know that F is force. Pressure is measured in newtons per square meter, which is a little bit bulky to be able to say, so we say it's a Pascal. Pascals are named after Blaise Pascal, who did a lot of work with pressures and fluids and things like that. He also is responsible for something in math called Pascal's triangle. Y'all can ask your math teacher about that one. A Pascal is a capital P because it's named after Blaise Pascal, and a lowercase a. So it's one of the first units that we've had here that has 2 letters for the abbreviation for it. So a Pascal is 1 Newton per square meter. Okay. So force of the book on the all right, so let's look at this. So we have the same book, 2 different situations. One it's laying down, one it's standing up. They have, if they're exactly the same book, the force of gravity on them will be exactly the same. But look at how much each book is in contact with the shelf below. This book is only in contact a very small amount, where this one has the entire back cover of the book is in contact. So because even though the forces are the same, the amount of area that is impacted here with the standing up book is going to be less, so the pressure exerted by that book is going to be greater because the area is smaller. Ooh, that sounds like an inversely proportional relationship. Well, let's see. Okay, you exert more pressure against the ground when you stand on one foot than when you're standing on both foot because you're decreasing the surface area when you pick up one foot. Obviously. Has your weight or your force due to gravity changed? Absolutely not. Smaller area supporting a given force, the greater the pressure is going to be on that surface. Okay, so you probably have seen somewhere. If you haven't, you should watch this little video that I have linked here. It's a bed of nails demonstration, and it's one of those things, the magical thing that sometimes magicians use, but as in most cases, it's not necessarily magic. It's probably something to do with physics. So a bed of nails is just a huge piece of plywood with a whole bunch of nails driven into it, about 1 inch apart, maybe less than 1 inch apart. And you probably have seen, if not, watch the video, somebody lay down on a bed of nails. And when you do that, you have to be a little careful getting on the bed of nails because you don't want your area to be too small when you're first getting on. So you kind of have to crab walk it back and then kind of lower yourself evenly onto the bed of nails. Once you're on the bed of nails, it doesn't puncture your skin because all your weight has spread out over all of these nail heads, and each the pressure of each nail is not enough to pierce your skin. However, if you stood up with your heel on one of those nails, it would certainly drive through probably the bottom of your shoe if you're not wearing, special shoes, and it would hurt you. So when you watch this video, don't attempt this on your own. I have to tell you that, because otherwise craziness ensued, and I don't want anybody to get hurt from physics. Okay, well, thanks for joining me. Have a great day.